Now let's talk about the mathematical modeling of our electrical systems. Till now whatever we have seen, translational mechanical systems and rotational mechanical systems. Now we'll see about electrical systems, and then we'll combine all together. That is most important. So now we'll see the electrical systems. So here you can observe a little carefully. So what are the elements that are there in the electrical engineering? Basically the three elements are there. One is resistor, other one is inductor, the other one is the capacitor, right? So now the property of resistors to resist the current, it is denoted by R and L and C. Suppose if I am sending some sort of current through this I am representing is I of t, and the voltage drop across this can be written as V of t. Similarly, if I am sending the current that through the inductor, the voltage that will develop across here also V of t. Similarly, the capacitor, suppose I am sending some sort of a current through the capacitor, so I am getting a voltage of the capacitor Vc of t. This is how it is happening. Now the voltage across the resistance can be written as V of t is equal to I of t into R. Similarly, the voltage across the inductor can be written as, so don't confuse that I am taking just V of t, but it is just like respective notations that I am taking, okay? L into d I of t by dt, and the capacitance Vc of t, so I'll write VL VR so that you'll get I'll not get confused anywhere. Vc of t is equal to 1 by C integral I of t into dt. So similarly from here, if you derive for the current, I of t is equal to V of t by R. So you might wonder why I am writing t. So when you try to draw a curve, so this is changing with respect to the time, whether you are taking current or voltage. So that's why I am taking. So when you are giving voltage which is changing with respect to the time, current also changing with respect to the time. So this I of t is equal to 1 by L integral V of t into dt, and I of t here is equal to C d V of t by dt. So that is how we can able to write the electrical equations. So in the similar domain, let us solve one particular example, and then we'll apply what the electrical concepts that whatever we are writing here, this how can we do it. Suppose I have a electrical circuit something like this. So this is plus and this is minus. This I am representing as E of t. Okay, so there is certain amount of resistance R. There is so I'll designate these values, say something like this. This is R2. There is some sort of a capacitor here. There is one more sort of capacitor here, and this is the voltage that we wanted to find out, say for example. So it could be AC system or DC system. For now I am just considering this. Our main intention is to find out the transfer function here. Say for example, this is my transfer function V2 of t output. Okay, so now say these elements are R1, this element is R2, this element is C1, this element is C2. So for this particular electrical circuit, I wanted to find out the transfer function. So transfer function Laplace of output, that is output here is V2 of S divided by Laplace of input. So here it is E of S. So that small e I am writing it as capital E of S. So this is the main agenda for this particular system. Now let us start step by step here. Electrical circuits are quite easy to solve according to me. Some people they may also find it very difficult to solve. So it depends upon how the perception of that particular people that they are thinking it. So for solving this, I'll put some sort of a rule that is called Kirchhoff's current law and Kirchhoff's voltage law. So in our if you see carefully, what we have written in our system is in the free body mass diagrams, the force acting on that particular body, we made it equal to 0. In a similar fashion, in the electrical circuits also, at any point the node that if we consider, the current is equal to 0 and the voltage in that particular loop is equal to 0, the similar thing. So for this particular system, what I am trying to note is, so this one I am trying to take as a particular node. Let me assume this is my node. Now here, so now I wanted to take the current in this particular node. Okay, so that is simple. So this I am just considering this as V1 and this I am considering as V2. This I am considering as V1. Now I am just taking the current. Okay, so for example, the current that is passing through this resistance, it is V1 minus E divided by R1, because the current that is flowing in this particular circuit is the difference of this potential and this potential. So the current flowing through the capacitor, C d V1 by dt, and the current that is flowing through the resistor, plus V1 minus V2 by R2 is equal to 0. So here one thing you have to be very, very careful. V1, whatever I am writing, it is V1 of t. Okay, V2, it is V2 of t. Okay, so now I'll take the Laplace transform on both sides. So I'm writing as V1 of s by R1 minus E of s by R1 plus, it is C1 s into V1 of s plus V1 of s divided by R2 minus V2 of s divided by R2 is equal to 0. So from this particular equation, what I'll do, I'll note that take V1 as common, V1 of s, if I take common, 1 by R1 plus SC1 plus 1 by R2 minus V2 of s divided by R2 is equal to E of s divided by R1. Okay, so this is how we are trying to draw at one particular node. Similarly, let us take the second node. Okay, so for this particular node, what is the current that is going here? That is V2 minus V1 by R2, whatever we have written for the same, I mean like free body diagram. Similarly, we are writing here C2 dV2 by dt is equal to 0. Now applying Laplace transforms, V2 of s by R2 minus V1 of s by R2 plus C2 s into V2 of s is equal to 0. From this particular scenario, I can write is V1 of s. So I'll write V1 of s, I'll take it is equal to 1 plus S into C2 R2 into V2 of S. Simple. So now let me substitute those values here. Then what I will get? So substituting those values into the system, what I will get? 1 plus S into R2, S into C2 R2, right? R2 into C2 into V2 of S, because whatever V1 is, this one, I am just putting that V1 here, into 1 by R1 plus S into C1 plus 1 by R2 minus V2 of S by R2 is equal to E of S by R1. So that finally indicates, I'll take V2 of S from this, what we need, V2 of S by E of S, right? V2 of S by E of S is equal to R2 divided by 1 plus S into R2 C2 into R1 plus R2 plus S into C1 R1 R2 minus R1. So that is how you can easily find the transfer function. See how simple it is to find the transfer function. Whatever it is, electrical systems. So all the electrical systems. So the basic thing that you need to understand is how we can make it so simple that we can easily solve it. Okay. So now, see, till now what we have seen is, you have seen the translational mechanical systems, you have seen the rotational mechanical systems, you have seen the electrical systems. How do you convert that into one particular common version? That is what it is called, transfer function version. Now let us see that transfer function of a armature controlled DC motor. See, this is one of the basic thing. In majority of the courses they will teach this armature controlled DC motor. Okay, so what we are trying to do here, we are trying to give certain amount of, so generally how it looks like. So there is a DC motor. Generally DC motor represents a circle with two brushes generally. Okay, and this is given with a certain amount of supply. Either you can give DC, generally you will give DC only. If you give AC it will not work. So this is the DC input, that let me take as Vs. The current that is flowing through the motor, I am taking it as IA, armature current. And this one, generally the motors are tied to certain amount of mass. Okay, this is having certain amount of inertia J, and it also may have some sort of a frictional coefficient B, and it may be rotating with an angle theta. So all these things you can observe carefully. We are giving electrical signal to a motor, then it is connected to a mechanical systems. Now we wanted to estimate, we wanted to find out the transfer function for such kind of systems. How do we find out the transfer function for such kind of systems? So to find out the transfer function of systems, first of all you should understand the electrical system and also mechanical system. So of course I think most of you are already studied about the electrical motor equation, so I'm just directly writing. So whenever you are giving supply to the electrical motor, the winding, whatever that you are doing, the winding is made up of with resistance. So when the current is flowing through that, it will convert into magnetic field, that is due to the inductance. So and it opposes its main field, that is what it is called the back EMF. So these are all the main electrical equivalent circuit of this particular system. So here the DC supply that you are giving, that is plus and minus. This is the DC supply that you are giving. That DC supply you can take it as armature voltage VA. The current that is passing through, they can take it as armature current IA. So the resistance here I am calling armature resistance RA, the inductance armature inductance LA, and the back EMF, so I am rating as EB. So the drop across this is plus minus, that is IA RA, and the drop across this is also plus minus. This can be written as LA DIA by dt, and obviously there is a back EMF that is there. So from this, using the KVL equation, whatever the voltage that you are applying VA is equal to, or you can say it is in indirectly the force that whatever we have applied is equal to the drop across IA RA plus LA DIA by dt plus EB. Okay, similarly, what we do, we will write the mechanical. So once the electrical, all the things that are related to electrical things are done, then the mechanical things are coming. So now what is the mechanical thing that is coming here? So when you are giving certain amount of electrical force to the motor, it starts rotating. So this particular system is having certain amount of mass and it is possess a inertia J. So that twisting moment of force is called the torque, and this angular moment is the theta. This J is also, he has told that there is some sort of a frictional coefficient is there, and that is with certain reference. Let us assume that is B. So for this, what is the equation that we will write? Okay, so the equation is here J into so for firstly T, right? So let me write the total torque T is equal to J into d square theta by dt square plus B into d theta by dt. Okay, and so this is very important, and up to this is fine. So you found the mechanical system of the motor, you found the Kirchhoff voltage law, and now we have to bring these two into certain common platform. What is that common platform? Is the torque, because the electrical and the mechanical, the common thing that is torque. So the torque generated by the DC motor is directly proportional to the current IA. So this can be written as T is equal to KT into IA. T is equal to KT into IA. Similarly, the back EMF, because that is opposing force, that back EMF is directly proportional to the coefficient. I mean, like how it is angular velocity of that particular shaft. So that if I remove the proportionality coefficient, the back EMF can be written as KB into d theta by dt, because it is the back EMF is again the dynamically changing. Now considering all those things, let us write the first of all the Laplace transform for all those things. So now firstly let us write the transfer function for this. VA of S is equal to IA of S into RA plus LA into S into IA of S plus back EMF EB of S. Okay. Now similarly the torque also you can write the same thing. Torque is equal to KT into IA of S, right? So we have written from here torque is equal to KT into IA of S from this. Okay, I am just writing is equal to J into S square theta of s plus b into s into theta of s. So from this, if I write the Ia of s is equal to j s square plus bs divided by kt into theta of s. Okay, very simple. Now for the EB, we can write EB of s is equal to kb into s into theta of s. So you can take this EB and substitute here also, and you can take Ia, substitute here also. See how simple the equations are. So that is how you can learn the equation, the simplicity of those equations you can learn easily. So substituting all those values, Va of s is equal to Ra plus s into La. So because I am taking Ia common, no substituting the Ia value there, that is Ia is js square plus bs divided by kt into theta of s plus Eb. Eb is equal to kb into s into theta of s. Kb into s into theta of s. That's how it is. Now our required function is, our required transfer function is what? Theta of s by Va of s. Now from this you take the theta of s into common and then do the some simple algebra here, then finally you will get this equation, that is theta of s divided by Va of s is equal to kt divided by Ra plus SLA into js square plus bs plus kb kt into s. That simple it is. So then multiplying both of them, and then you can take into different forms. You can take s square and s into constant form. You can take, that is kt by jla, and you can take s square into common, s by taking s, and s square plus jra plus bla divided by jla into s plus BRA plus KBKT divided by JLA. I mean something like this you can simply take into this particular form. Okay, so this transfer function can be written as, theta of s by V of s is equal to KT by something like this. You can also write. So there is no big difficulty in doing these things. In other way also, some people in some textbooks, they may also write these things as KT divided by RA plus SLA Js plus B. So here what they will do, they will take RA as a constant. When they will take a constant, S into LA by RA plus 1 into BS into 1 plus js square by bs, they take common, plus kb kt into s. That is can be written as, now the ta is the la by ra, tm is the j by b. So that also generally people something write, that is kt divided by ra into b. So because ra into b, if you take into here, s if you take common, so 1 plus s ta. Ta is La by Ra, 1 plus S Tm, Tm is J by B, plus Kb Kt divided by Ra into B. So there are so many ways the people are writing this particular transfer function. So whatever you understand up to this particular point, it's also fine. you know, you can easily do a lot of analysis with this help of this particular analysis. Similarly, you can do the transfer function of a field controlled DC motor also. Now we'll see the transfer function of a field controlled DC motor. That is transfer function of a field controlled DC motor. It is as simple as whatever we have did in the armature, same thing, but the field here is externally given. So here, so simple, the equations will be more or less like the simple things. So here what will happen, the speed of the DC motor is directly proportional to the armature voltage and inversely proportional to the flux. Actually, in the field controlled DC motor, the voltage is kept at constant, the speed is varying by varying the flux of the machine. Since the flux is directly proportional to the field current, the flux is varied by varying the field current. So the speed of this control system is an electromechanical control system. Okay, so let us draw the complete again the same drawing, but the field is not there, so field will be separately here. So that's why the mechanical diagram will be looks something like this. I mean electrical diagram. First draw the electrical diagram. This is plus and minus Vf. The constant is Ia, and it is having a mass, and it is running the load J and B. So that is having a theta. So it is having La and Ra as the inductance. Obviously you know that. So that one I am trying to redraw. So it is having so equivalent field circuit I am drawing. Field circuit is field resistance is Rf, and field inductance is this thing Lf dIf by dt, because the field is separately, right, and here it is there. So the voltage that I am giving here is the field voltage Vf, and the current that is flowing through is If. So this equivalent circuit you already know what we have seen earlier. This is the equivalent circuit for the field, because the field is given with a small inductance value, and I mean required inductance value. So now for this particular thing you can write as Vf is equal to If into Rf plus Lf into dIf by dt. Okay, so you already know that from this all these equations, torque is directly proportional to the field current. So that is written as KTF, the constant, into the field current If. So the mechanical equations that you already know, that torque is equal to J d square theta by dt square from all our earlier thing, B into d theta by dt. You already know from our earlier equations that already you know these things. Now equating all those things into this particular field thing, so the field system, so what you will get here, Vf of S is equal to Rf into If of S plus Lf into If of S. So the torque T of S is equal to K Tf into If of S, that is also equal to J S square theta of S plus Bs into theta of S. So taking all those into considerations and equating both of them, so what we will get from here, is KTF If of S is equal to j s square theta of s plus v s into theta of s. So from this, I of s is equal to s into js plus b by ktf into theta of s. So substituting this value into the theta of s into this particular item I of s, whatever it is coming here, we substitute here. So what we will get here, so we are getting something like this here, that is Rf plus s into Lf into s js plus b divided by ktf into theta of s is equal to vff s. So from this, theta of s by vf of s is equal to ktf divided by s into rf plus s lf into b plus sj. So that is also, you can, in terms of motor gain and all those things you can write, but this is how we can write the equation for the control system.